Welcome back. It's Intro to Physical Anthropology. I'm David Leitner. I am your instructor. Today, we are going to talk about fossils and the geologic timescale. We talked a little bit about the geologic timescale in the first week of class, but now I want to sort of expand on that a little bit. Give us some idea of sort of the time scales of evolution we're looking at when we're looking at primate evolution and ultimately human evolution as well. So, but to begin with, we need to start with some basics, like the fact that the Earth is old. Hopefully that's not news to you. It is extremely old, but how old exactly? Well, I showed you the video on the Canvas website earlier this semester of the demonstration where they measure out the history of the Earth on a football field. I want to do something very similar, but we're going to use a slightly different scale. On my scale, we're going to do 1 inch is equal to 1 million years. Okay? Just to keep the math a little easier. On that scale, standing where you are right now, pick any direction, and the universe began over 1,100 feet away from you. 13.7 billion years ago. That was the Big Bang. The Earth doesn't form until almost 375 feet away from you. So there's 2/3 of the life of the universe there. That you're dealing with. From the beginning of the Earth to the time of our oldest fossil evidence for life, this doesn't mean it was necessarily the first life forms, but it's the first life forms that left fossil evidence for us to find, is somewhere between 316 to 283 feet from you. That's 3.4 to 3.8 billion years ago. So, really, life begins almost as soon as the Earth cools enough for liquid water to exist. However, complex life like dinosaurs takes much longer to get started. The dinosaurs don't even appear until 19 feet away from you. That's quite a lot of distance here compared to the beginning of the universe, which is, 1141 away from you. The dinosaurs stick around until about 5 feet 6 inches from you. Primates first appear about 5 feet from you, so very soon after the dinosaurs disappear. As I mentioned last time, mammals have a big adaptive radiation into all the niches the dinosaurs left unfilled. But even with that, it takes until about 6 inches from us before the last common ancestor between chimps and humans. So the beginning of the hominin line, that is the line that leads to us. Genus Homo itself only begins about 2 inches from us. That's 2 million years ago. The first signs of agriculture are about 1/100th of an inch from you. And the Common Era, right? We measure from about 2021 years ago. Well, that's about 2/1000ths of an inch from you. So these are the timescales we're looking at in terms of evolution. Bear those in mind, because evolution and even the geologic changes we're going to talk about in this chapter don't occur overnight in human terms, but are very rapid in terms of the history of the universe, or even just the Earth itself. So, if you're interested in digging into this topic a little deeper, here are a couple of... go ahead and pause and copy these resources down. HHMI has a great interactive slideshow on deep history. They also have this great interactive app called the Earth Viewer, which you can actually sort of rewind plate tectonics and see all the land masses come back together, as well as looking at how things like climate has changed, the temperature of the Earth has changed over time, concentrations of oxygen or CO2 in the atmosphere, all sorts of things. It's really, really neat. And then ChronoZoom is another sort of great website. It's more of a sort of timeline thing, but you can sort of zoom in on certain parts of the timeline very easily and see what was happening at that point. So these are fun things to sort of play around with. It's not an assignment, but I highly encourage you. Okay, so the GTS, the Geologic Timescale. As I might have mentioned before, what I'm representing in front of you, if you look at the time segments down below, you'll notice they're not even. This is sort of a logarithmic scale in the sense that the time segments actually, even though they're all sort of relatively evenly spaced, the actual time distance between each line is much longer than it would seem. Oh, excuse me. And remember, we divide the geologic timescale up not by years and months and decades and centuries, or millennia even. We look at eons, eras, periods, and epochs. And sometimes we subdivide the epochs as well. What marks things off on the geologic timescale is not the absolute passage of time, but significant changes in the geologic strata. That is, when we see a change in the rocks, that's how we know we've reached a new point in the timescale. Okay. I won't make you memorize these today, but you'll want to do that for the exam for sure. We are currently in the Phanerozoic era, eon. Living in the Cenozoic living in the Cenozoic era. We are going to be looking today at both the tertiary and quaternary periods. Sometimes referred to, the tertiary is divided into the Paleogene and the Neogene. And then really our biggest interest when it comes to human evolution is going to be the late Miocene, the Pliocene, the Pleistocene, and the Holocene. And what we're living in now, a lot of geologists have proposed a new era, though its actual sort of when it begins is debated. Some people say 2,000 years ago. Some people say the beginning of agriculture. Some people say no, not really until sort of the Industrial Revolution. There's some disagreement, but they all sort of agree it's happened within the past 10,000 years at some point. That human beings have created such enormous changes on this earth that they will be visible in the geologic strata for millions of years to come. And future geologists will be able to date things from this period based on the changes they observe in the strata that we caused. And so it's called the Anthropocene. So how do we know about the past? Excuse me. Our chief information about the past comes from fossils. But what is a fossil exactly? The technical definition is very straightforward. It is ancient, organic hard tissue remains that have completely mineralized through the process of fossilization. Now, when we're talking about human evolution, not everything is old enough to have actually completely fossilized. And so we use oftentimes a looser definition in these contexts, in the sense that it's really any ancient that is greater than 10,000 years old organic remains, or other traces of organic life that we can find. That doesn't mean fossilization isn't important. It is. But as a matter of art, we're sometimes a little loose about using that term when we're talking about different kinds of artifacts. Fossils themselves are the only direct evidence of the past, at least prehistorically. But the fossil by itself is not that useful. I mean, it's still useful for a lot of things, but you really want the context the fossil is found in as well. that tells you a lot more, not just about the fossil, but about the world the fossil existed in when it was part of a living creature. It's important to remember, too, as we're going to find out, the process of fossilization is... luck is a big part of it. What gets fossilized depends on a whole bunch of different factors. And so fossils are not a random sampling of past life. Some things are much more likely to fossilize than others. Some places are more likely to provide fossils or provide the conditions for fossilization than others are. So it's not a complete random sampling. So we shouldn't mistake we shouldn't base our estimates of ancient life solely on the presence of the fossils. We have to be a little more thoughtful about the way we go about that. Now, there are lots of reasons fossils may not be discovered. One of them is that very few things actually become fossils. A lot of things, like jellyfish, lack hard tissue remains. There are very rare instances where soft tissue impressions can be preserved in silt that then becomes sandstone. Very, very rarely, though. Most things that lack hard tissues decompose or erode completely before they get buried. Things, even hard tissues, can get trampled. They can be digested by predators or scavengers. They can be scattered by scavengers. In fact, there's so much that can happen to remains that there's an entire field called taphonomy devoted solely to the study of what happens to remains after death. So the take-home here is only a fraction of fossils get found. So even if something has the luck of becoming a fossil, going through fossilization, there may not be a person walking by when it comes to the surface. Remember, erosion is constantly going on and revealing new fossils, but as soon as they're exposed, they can also erode themselves. So there are millions and millions of fossils under our feet that we're not going to know about because nobody's thought to dig there, or there's no good reason to dig there right now. So these are all factors that can prevent things from becoming fossils. In addition, only the most durable materials actually fossilize. So the most likely bones to fossilize are long bones, jaw bones, skulls tend to have larger segments in them. Teeth, as I've mentioned before, are pre-mineralized. They're already mineralized, so they're living fossils in your mouth right now. We find them a lot in the fossil record because of that. But small bones, like the bones of the fingers, ear bones, things like that, aren't nearly as likely to remain in the fossil record. They get lost much more easily. They're smaller, so they erode faster. So, the main thing is that an organism needs to be buried shortly after death in order for fossilization to begin, because you have to arrest the decomposition process. Most of the bacteria and other microorganisms that decompose your body require oxygen. Quickly burying something deprives the body of those organisms of the oxygen they need to do what they do. It also helps to prevent from erosion, scattering, and trampling that could sort of pulverize the remains. So the way this usually works is there's some sort of sedimentation event that occurs. In this case, say a hominid dies next to a lakeshore, okay, where maybe they went to get some water, but they were sick and they didn't make it back from the lakeshore, so they die on the shore. It doesn't have to be a lakeshore. Lakes are great because they drop sediment constantly. Floods drop sediment rapidly. But volcanoes are great source of fossilization as well. Dust and volcanic ash can bury things very quickly. After soft tissue remains decay, they don't have to decay all the way, by the way, but as long as the skeleton is still intact, it gets buried through sedimentation. Maybe the water level of the lake rises, maybe a volcano, maybe a flood. Something happens that sort of buries these things. The next step in the process of fossilization is petrification. So this is when the minerals in the bones are exchanged for the minerals in the soil surrounding it. This is a very slow process, and literally petrification means turning to stone. Interestingly, this process was first proposed, back in 1669 by Nicholas Sterno. Which is amazing because doesn't seem like an intuitive thing, right? That something could turn to stone by leaching minerals from the soil. Eventually, after petrification, the strata that the fossil is buried in will be exposed by erosion, usually in some way. And if we're lucky enough to have an archaeologist or paleontologist or paleoanthropologist in the vicinity at the right time to spot this, we can recover that to the laboratory and study it. Now, some things we call fossils that aren't properly fossils are also very helpful in telling us about the past. Oftentimes, these will involve the preservation of soft tissue. Frozen specimens, particularly those recovered from mountain caves where the air is cold and dry, or from frozen tundra in the Arctic or in glacial areas. These provide great opportunities because what essentially happens is the soft tissue freeze dries and is preserved. This is the remains of a woolly mammoth discovered in just the last 10 years, actually, I think it was, in Russia, and it is extremely well preserved, as you can tell. One of the really interesting things about this is we've known about these preserved specimens for hundreds of years. So much so that, in fact, during Victorian times, even into the early 20th century, there were dinner clubs in parts of Europe for rich men, mostly, where they sort of reveled in eating strange things from all around the world. So whatever an adventurer came back with, they would eat. And the number of freeze-dried woolly mammoths that were eaten, and mummies too. Oh, they ate mummies. Yeah. Not good. It's sad though, because all that stuff is lost to us now. But there's new stuff popping up every day. This is a child found in a probably an Incan site. It was found in a sealed off cave with 2 other children as well. And the child was actually sacrificed, though we're not entirely sure why. It's a 7-year-old, and as you can tell, the skin is incredibly well preserved. There was no sort of efforts at preserving the body beforehand. They didn't remove organs like they do in Egypt. It was simply sort of placed in this cave, and the cold, dry air sort of dried it out and preserved it. Another common source are bog bodies. We find these in Europe a lot, especially Celtic and pre-Celtic civilizations. Um, these bodies are mummified as well, but not through drying or preparation. Rather, these bodies, again, oftentimes sacrifices, are found in bogs, peat bogs. Peat bogs are highly tannic, acidic bodies of water, with lots of vegetation. The acidity in the water essentially tans the skin, tans it like leather is tanned. And that preserves it. It makes it tough and preserves it. It preserves it so well, in fact, that not only can you see this man's stubble, but you'll also notice tied around his neck is the garrote that was used to strangle him. We think most of these were sacrifices of probably kings, actually, or chieftains of some kind of leader. Probably as an offering after periods, during periods of famine or drought. It would be taken as a sign that this leader had been failing them, and to appease the spirit world and the gods, the king would be sacrificed. And so we have these bodies that pop up in Germany, in the UK, and in other places where there were large peat bogs. Finally, we've got a type of fossil called a trace fossil. Trace fossils are not the organism itself, but evidence of the organism that was left behind. Footprints. These are the famous Laetoli footprints laid down in volcanic ash shortly after an eruption in I think near Lake Turkana in East Africa. What's really interesting here is that we not only get a great sample of at least two individual hominins, we think Australopiths. You can tell that they're two different sizes, so it may have been a male and a female, it may have been a parent and a child. But we also get the footprints of lots of other animals that cross the same place at the same time. So they must have crossed while the ashfall was wet. There may have been a rain shortly after the ashfall. So it was like wet cement, and walking across it, you will leave these footprints, and when the sun bakes it dry, it's like cement. That gets covered over, we come along and uncover it millions of, I think these are 3.66 million years old. My other favorite trace fossil is the coprolite. Coprolites are fossilized poo. There's no poo left in them, so don't worry. They don't smell. I wouldn't recommend it, but you can lick them. It's fine. It's safe. Rather, it's no more dangerous than licking any other rock. They are great because they not only give us, help us identify, different species that were present if we don't have their bones, because different kinds of animals have very characteristic scat. We can also tell a lot about what they were eating by cutting into these things and looking at what we find in there, because it's poo. So everything you would find in poo is in there, and we can discover a lot about their diet that we would otherwise just be guessing at. This is direct evidence of what ancient animals are eating. Okay. I'm going to leave it there for now. That is how things become fossils. In the next video, I'm going to talk about stratigraphy, which is the study of geologic layers, and helps us give context to these fossils when we find them. Until then, I hope you are taking care of yourself. Have a great week, and I'll see you soon. Bye.